the third practice for this week. And this one goes back to, and I hate to say this, but for those of you who remember honors chemistry, the second trimester, this goes back to chapter 9 for the most part. So you're going to have to check out some of these topics in chapter 9. One or two of them, like this one we're talking about right here with the Lewis dot diagrams, I think it's chapter 8. I have to check that though, but you can find all of this stuff in the book, in our white chemistry book. It's just that it's kind of spread out a little bit. So I'm going to do my best to explain each part. So this video may not be like my shortest video. Okay, give me 1 second. Sorry. Okay, so in the boxes provided, draw the complete Lewis structure. That means with the dots, right? The electron dot diagram for each of the 3 molecules represented below. Now, let's take a specific look at CF4, and I'm going to fast forward here to a regular periodic table. So the question becomes, like, how do I know what to do with CF4? Well, CF4 is going to look like this. I'm going to look to see how can I write the dot diagram, and for most of you, just a quick review is going to be enough. Each of the symbols for a dot diagram has 4 sides to a box, just like this, and it's dotted because that box is imaginary. And how do we know how many dots carbon should have? How many extra valence electrons? Valence means the outside most valence, outside most electrons. Carbon has 6 electrons, but only 4 of them. And how do I know that? Well, I start here on the left-hand side and count 1, 2. I skip over all of this and then go 3, 4, 5, 6, 7, and then eventually 8. Now, if we do 2, so what I do is I start anywhere. It doesn't matter where I start, which side of the box I start for carbon, but I start putting electrons, and right now I'm using numbers, but in actuality what it's going to look like is this. So 1 goes on each side of the box first until I have to pair them up, and I can fit a total of, so if I go 1, 2, 3, 4, the 5th one will be here on the same side as the first one, the 6th one will be on the same side as the second one, the 7th the same side as the third one, and then of course the 8th the same side as the 4th one. And that's how I include my electrons that way. So the electrons are negative and repel each other, and they have to spread out first. So for carbon here, notice I have 1 on each side of the box, like that. Notice that F, fluorine, is over here at 7. 7 means, and it doesn't matter where I start here, 1, 2, 3, 4, 5, 6, 7. Notice that I have 3 pairs of electrons. Those are relatively stable, and then I have 1 extra one that is for bonding. Okay, so if you have single electrons, they are for bonding for the most part. Okay, so notice that if I do this 3 more times, like this, I can bond here, here, I'll bond with the fluorine up there, and I'll bond with the fluorine over there. Because I have 4 fluorines, and I have 4 single electrons for carbon. Carbon is what we call the central atom. Okay, so I'm going to erase this stuff with carbon and fluoride, and just so that like I can use this from here on out. That's a 3, I'm going to just get rid of this here. 8, 7, 6, 5, 4, and 3. So that's how we know how many electrons we have. Okay, so I go back here and I do exactly what I did before. I got carbon, I got 1, 2, 3, 4. I have fluorine, I got 1, 2, 3, 4, 5, 6, 7. So it looks like that. I do the same thing for all of these, like this, and like that, like that. And that's my Lewis dot diagram, okay? So I'm going to ask you, I'm going to show you one more. I'm going to ask you to do this one on your own to make sure that you can do it yourself. We'll take a look at another one. Where's sulfur? Sulfur is number 6. It's in row 6 right here. So just because it's below oxygen doesn't mean that the number of electrons, the valence electrons, change. It does not. So oxygen, sulfur, selenium, tellurium, polonium, and livermericium All of these have 6 valence electrons, no matter where they are in the group, as long as it's in group 6. Wrong way. There we go. So that means that I start here and go 1, 2, 3, 4, 5, 6. Notice that I have, now here's something that we need to do. Sometimes when you have a paired sets of electrons, notice that according to the single electrons, this should actually just be SF2. But because I have 2 extra fluorines, come on, where's my, there it is. Because I have 2 extra fluorines here, I have SF4. What I do is I pair fluorine this way, like that, fluorine this way, like that, and then it doesn't matter which one I take, but I take one of the pairs of electrons and I break it up to fluorine this way, like that, and I break the other one down, fluorine like this. Okay? I wanted to make sure I showed that to you so that you could see that even if we have electrons that are paired, what happened to the other? There. Even if we have electrons that are paired, we can still break those up and still bond them to things. And you're going to have to do that with PF5. Okay? So let's move on past that to here. So let's do, this one is on the basis of the Lewis structures drawn above, answer the following questions about a particular molecule indicated. So what is the FCF bond angle? So it looks like you would say, well, that bond angle right there is 90 degrees, of course, but it's not, though. See, remember that these molecules exist in three dimensions, not 2 dimensions. So it's not 90 degrees, it's actually worse than that. So I'm going to refer you to this page right here. Now take a look at this. They use perspective drawings over here. I'm looking for the one that looks like CF4, and that would be this one here. That's called a tetrahedral configuration where we have 1 central atom and 4 other atoms that are off of that, bonded to it. Tetrahedral looks like this here. This is called a perspective drawing. Okay, that means that it is not, notice it doesn't look like a cross like the other one looked like that. It's not that. Notice that there's an angle here that is not 90 degrees. Actually, when you put a central atom in the middle and then you put things off of it, it actually looks more like almost like a pyramid or something. And because it looks like a pyramid, that means the angle then is 109.5. Okay, we'll talk a little bit about the, wrong way. Let me go back to this one here where it says, what is the FCF angle in CF4? It is not 90 degrees, okay? It is 109.5 because what we have is tetrahedral shape, okay? A tetrahedral shape. That's an object, a 3-dimensional object that has 4 sides. That's what it is. If you've ever seen 4-sided die, and yes, there are 4-sided dice, that's what it is. What is the hybridization of the valence orbitals in the P and PF5? Well, let's go to this again. I need to look for something that has the same basic shape as PF5, and I see it here. I see PCl5, which is the same as PF5. This is called trigonal bipyramidal. There are 5 bonds from the central atom. Okay, it's trigonal bipyramidal. It looks like this. You have axial bonds here, and then you have equatorial bonds here, here, and here. Okay, so take a look. This says right here that the hybridization for 5 bonds, there's 1 that's an S, there's 3 that's a P, and there's 1 that's a D, and when you add these all up, that equals the 5 bonds. So sp3d is the hybridization. So let's go back. So for this, it would be sp3d. I guess I could do the, they usually do this with small letters, sp3d, like that. Okay? Notice that the hybridization for a tetrahedral always is sp3. We're missing one of the end bonds because it's 4 bonds, 1 s and 3 p's, instead of 5, which is 1 s, 3 p's, and 1 d. Okay, what is the geometric shape formed by the atoms in SF4? Now, if you remember, what this looks like. The SF4 looks like that. And then I count up the number of bonds and lone pairs on the central atom. The central atom is S because it's the least electronegative and it's the one that comes first. So almost always the central atom is the first one in the formula and it's the one with the least electronegativity. And everything has less electronegativity than F. So I count 1, 2, 3, 4, 5. So that means what I have is trigonal bipyramidal. We just saw that with the PF5 bipyramidal. Okay, but this is saying what is the geometric shape formed by the atoms. When one of them is a lone pair like this, that changes the shape. So let's go back to see what it says. My chart says for the where are we at here? SF4 is actually right here. So it's trigonal bipyramidal, but this is called seesaw because the one bond that goes away, notice that B bond right there? Well, that's now a lone pair and doesn't show up. So it looks like you got a seesaw standing on end. You have the board for the seesaw there. You have the supports for the seesaw there. That's why it's called seesaw. Okay, if you hold it another way, it looks like a hot dog, kind of. Okay, so all right, so this is actually, if we're talking about what geometric shape is formed by the atoms, which means only the bonds, and what we would say the correct answer to that would be seesaw, and I think there actually is a dash in between. So seesaw is the correct answer. Seesaw is a derivative, though, of the trigonal bipyramidal shape, where there are 5 things connected to the central atom. I'm going to stop there and continue on with the next